Welcome back to Algebra 1. So in exponential growth and decay, we have a specific way that we look to decide if it's growth or decay. If we take a look at these, we should be able to tell. So in this first problem, because it is larger than 1, it is growth. It is larger than 1 by how much? 0.2 or 20%, so it is a 20% increase. The initial amount would be any number that is not taken to the exponent, so in this case the initial amount is 1. In the second problem, it is decay. I subtract my base from 1 to determine how much of a percent I'm decaying. That's going to be 0.22, 20%, 22%. And the initial amount again is 1. This is less than 1. It is also decay. Less than 1 is also decay. Initial amount is 1, and the decay amount is 3/8, which is about 37.5%. This one has an initial amount of 28. I have a growth of 3%. So those are places that we look in the traditional model for exponential growth or decay. We are going to have a different model today. And that other model will use something called the natural base, or E. We'd love it for our money in the bank to actually grow every nanosecond continuously. And that actually is possible if we use this natural number. It's another irrational number like pi. It's called the natural base E. So surprisingly, there's a lot of other ways to count besides counting by tens. We count by tens, we have 10 digits, we think that's the only way to do it. It's not. Computers actually only use 2 numbers. Computers only know 0 or 1, off or on, for switches. That's why they use base 2. So if we're counting in some other numeric base other than base 10, our 0 will be 0, our 1 is still going to be 1, and now everything changes. 1, 0 means 1, 2, and 0, 1s. That is how we say the number 2 in binary in computer language. 3 is 1, 2, and 1, 1. 4 is 1, 4, 0, 2s, 0, 1s. 5, 1, 4, 0, 2, 1, 1. Every single one of these numbers can only go up to 1, and then you have to put it in the next space. So 16 looks like 10,000 to a computer. This is counting in a different number base than we're used to counting it. There's actually a different number that's even more important, and it's called E. It's like pi, which is irrational, I, which is imaginary. It was discovered by Leonard Euler. A couple other people figured out what it was, but Euler actually determined how to get there, what the number was. It is called the natural base, and it's just like pi, 3.1415 continues. This number continues. So we have a button on a calculator for these things. Now, pi came from a circle. It came from circumference divided by diameter. E isn't based on any shape. It's based on continuous exponential growth. It is actually the main number in calculus. So because of that, it's used in financial equations, it's used in gaming, it's used in a lot of statistics and almost everything that goes on in calculus. There are 2 huge ideas in calculus. One is the area under a curve, the area under any shape bounded by first number, starting number, and ending number. And it's the slope of a line at any point, instantaneous slope. Those are the two huge ideas in calculus. And E really ties this all together. E is a base, so we are going to treat it like a base, and we're going to use the exact same rules that we have used when we are multiplying exponents. We add the powers. When we are dividing exponents, we can divide the numbers in front. With the exponent, what we do is subtract the powers. Minus 4 is 1, so we don't have to write that. When we are taking anything to a power, we have to take the individual things to the power. So 3 squared is 9. E to the, this is all going to be taken to the power by multiplying. Negative 4 times 2 is negative 8. X, multiplication we add the powers, division we subtract the powers. Power to a power is where we multiply the powers. When we have a base of E, no matter what the base is E, we have to have a way of showing growth versus decay. Where we show that is in the exponent. So our equations are completely different. You need to make sure that you have this down. This is the equation that we're going to use. We have R now. A is still our initial amount. R, a number in front of X. If R is positive, any positive number, including decimals, we have growth. So here's our first 2 points, 0, 1 on the graph, and 1, E. Graph looks like exponential growth. When we have a negative exponent, what happens is because we make that exponent, when the exponent is negative, we make it a fraction. So this point right here becomes 1 over E. All of the rules for exponents apply. And this is how we get growth versus decay. We're now looking at the exponent. If the exponent is positive growth, if the exponent is negative decay. So when we're looking at these, you're probably going to do more calculations before you try to figure these out on a t-table. So I'm going to take a look at X here, and I'm going to change it a couple of times. When I plug in a 0, E to the 0 is 1. I'm going to have a starting point on my graph. So my starting point now is where I am on this graph. And then when I plug this in, I'm actually going to multiply 3 times 2.71, etc. And I go up to approximately 8.1. In a decay graph, because my starting number here is 1, I'm going to start at 1, and I'm going to figure out one number before and one number after 0. So I'm going to plug in -1 and +1. And one of those should be above and one below. Because this is negative point. So how do I tell whether it's growth or decay? I'm looking at the exponent here. The exponent is positive. This is a growth. Exponent is negative. That means it's decay. Exponent is positive, larger positive. This is a growth. What would our next step look like? Well, this first term here and here, A and A here, those go on the y-axis. So on this particular graph, I'm going to go to 1/2. On this graph, I need to go up to 4 with room to spare to go up. I know it's exponential in one direction. And on this one, I will go to 2. So A gives us 1 point on the graph. Our second point is we need to do whatever exponent we have on E and what those we're going to multiply each of those. I'm just number crunching along the side in a calculator, and when I do 1/2 times e to the -1, I'm going to get 0.18. So that's about 0.2, so I'm going to go about here. When I plug in 1 into the equation 1/2 e to the first power, that is going to give me 1.39. Approximately in here, and my graph is exponential growth. I plug in 4 here in the equation. I'm going to plug in a 1 and a -1. When I plug in a 1, I get 1.5 approximately. When I plug in -1, minus a -1 becomes +1, and my graph goes up to approximately 10. I'm getting 3 points on the graph and able to make the curve from that. So I do want to show you when I have the graphing calculator, 2 times e to the power. In my particular calculator, it does come up with parentheses already. So I am safe to type in multiple things in here. I could have just, yes, I know that's 2. I could have just put it in 2 and a -2. But in this case, I'm going to go down to less than 1/4. And when I go in the other direction, I'm going way up to 14. So use a calculator. You need to in order to use the E button. On our calculator, see this little LN? It's above that, so I'm going to do blue LN, and that's going to give me my E. So one of the huge equations we like, which is amazingly simpler than the last equation that we got, is continuously compounded interest. A equals P, e to the RT. The only things that we need to plug in are the principal, and the rate doesn't get added to 1. It just gets written as a decimal. So when we look at those and we're coming up with things, here's our equation, and this is our graph. We're trying to figure out what it would take to be 10 years growth. Notice this 0.04, that's a 4% growth. Starting amount, how much do we plug into the account? So we plug in a 10 here. This E is going to be a calculator button, and what you find if you look at the graph at 10 years, we're at about 7,200, 7,250. So if we need to set these equations up, we need to think, what is my initial amount, which is called my principal. The only thing I need to do to change my rate is make sure I put it in as a decimal. So this is going to be 0.05, and for 10 years. That equation becomes P equals E RT, RX or RT. So number crunching that, you do need to make sure that this entire thing goes in the exponent. It's an easy mistake to make. It is a really good habit to put that in parentheses. I could also put that in parentheses with a times. But it's a simple habit, good habit, that will make sure that you're getting the right numbers, especially since with this E, you don't have a good idea of what that might look like. So I would do the good habit. And when I do that, I get $7,007. So we earned 5% interest on a little bit less money and almost to a friend. Turns out the percent interest that we can collect, if we divide that number into 72, this is called the rule of 72, you'll probably hear it in personal finance. In the rule of 72, if I can get 5% interest, I divide 72, that tells me how many years it takes for me to double my money. So in this case, it would be a little bit over 12 years. So you're going to use the equation, you're going to see growth and decay. I'm expecting questions on this. This is very different to you on Tuesday, and have a good day.